Welcome back, and welcome to the amazing world of the thin shell, a unique type of structural element that's found in some of the modern world's most exciting buildings. Just to whet your appetite, here's a typical example. Chapel Lomas de Cuernavaca, built by Felix Candela in 1958 in Mexico. The parabolic arch that forms the front of this chapel spans over 100 feet, and it's nearly 70 feet tall. Yet the concrete shell itself is only 1.5 inches thick. That, my friends, is a thin shell. Now, to understand what makes thin shell structures so special, let's do a simple experiment. Suppose I asked you to use this single sheet of paper to create a cantilever beam that's capable of carrying this pen. Well, if you tried to do that by holding the paper flat, you wouldn't be able to carry much load at all. The paper's just too flexible. But I think if I gave you the mission, you would almost instinctively take the paper and form it into a slight curve. And when you did that, you would find that you're able to support the pen with no difficulty whatsoever. The only difference between the piece of paper that can carry the load and the one that can't is curvature. A thin shell, then, is a structural element that attains both strength and stiffness primarily from its curvature. The paper shell in my demonstration was strong because it was able to carry load without failing, and it was stiff because it didn't deform much under load. Thin shell structures can be made of just about any material: wood, masonry, steel, plastic. For example, during World War I, several German aircraft manufacturers used molded plywood shells for the fuselages of fighter planes, like this one. Later in this lecture, we'll see a traditional Spanish vaulting technique called the timbrel vault, a thin shell made of ceramic tile. But since the 1920s, the finest structural examples of thin shells have been concrete, because the complex curved shapes that characterize thin shells can be attained much more easily in concrete than in any other material. And once again, the key to concrete's success is its versatility of form, the ability to pour a semi-liquid material into a curved mold and then have it harden into a rock-like mass with that same curved shape. It was the great 19th century mathematician Carl Gauss who proved mathematically that any curved surface, natural or man-made, can be characterized as only one of 3 different possible shapes, as cylinder-like, dome-like, or saddle-like. All 3 of these geometric shapes can be used as the basis for thin-shelled structures. Here's an example of a cylinder-like shape, essentially a semicircle extruded out into 3 dimensions. As you can see from the grid that I've superimposed over it, a cylinder-like shape has curvature in one direction only, no curvature at all in the other direction. And you can tell this because the longitudinal lines on the shape are straight. My paper cantilever was a cylinder-like shape because it curved in only one direction. Here's another cylinder-like shape, in this case generated not from a semicircle but from a parabola. In structural applications, a parabolic cylinder would generally be more efficient than a semicircular cylinder, for exactly the same reason that a parabolic arch is more efficient than a semicircular arch. These are dome-like shapes, one semicircular and one parabolic. Note that a dome-like shape has curvature in both directions, and both curvatures are oriented the same way. In this case, both are concave downward. And finally, a saddle-like shape, shown here, also has double curvature, but now the 2 curvatures are oriented opposite of each other. One is concave up, and the other is concave down. So how are these shapes used in great structures? Well, the Chapel Lomas de Cuernavaca, which we saw at the start of this lecture, is a saddle shape. And in previous lectures, we've seen dome-like shapes in the domes of the Pantheon and Hagia Sophia. And we've seen cylinder-like shapes in the vaults of Roman and medieval buildings. But these latter examples are quite thick, and so they don't really exhibit the extraordinary load-carrying characteristics and structural efficiency that we'll see in thin shells. If you'd like to see an example of a true thin shell structure, well, you need go no farther than your own refrigerator, where you're probably likely to find one of these. Now, you may think of the eggshell as the epitome of fragility, but in practice, it's actually astonishingly strong when it's subjected to a uniform loading. So if I press on the egg from all directions, in compression, it's capable of carrying a tremendous amount of load, in very much the same way that a shell-shaped roof would experience uniform loading distributed over its entire surface. Indeed, the egg is such a fine example of a thin shell structure that it was actually used as the standard for thinness in one of the great structures we'll be looking at later in this lecture. The saddle-like shape is known mathematically as a hyperbolic paraboloid. Geometrically, it's formed by extruding a parabolic shape along a parabolic path, like this. The intersection of the three-dimensional parabolic shape with the horizontal plane then forms a hyperbola here, and that's why it's called a hyperbolic paraboloid, or HYPAR for short. The HYPAR is particularly well suited for roofs because its double curvature provides exceptional stiffness and strength, and just as importantly, because this highly complex shape can actually be generated with a series of straight lines. Here's a model of a HYPAR roof that I cast from concrete. And here you see that shape we saw earlier described as a purely geometric shape. Here it is in more concrete form. Up front you see the parabolic shape that's the basis for the overall geometry. And then in this direction we can see how that parabola is extruded along a parabolic path, forming the second degree of curvature, which is now concave in the upward direction. And then finally we see the intersection of the curve with the horizontal plane down here, forming the hyperbolic curve at the base. A HYPAR carries load primarily in compression. It works very much like an arch. When we see it in this direction, it looks exactly like an arch, and downward loads cause load to be transmitted in compression out to the supports. In this direction, it's actually possible for the HYPAR to experience some tension, because, as you can see in this direction, the shape looks somewhat more like a cable than like an arch. The amount of tensile stress is quite small, though, and so we typically don't have a problem with HYPAR shapes in concrete, even though concrete has very limited tensile strength. Perhaps the most important aspect of all thin shells, and the HYPAR in particular, is because of their thinness, they experience little or no bending stress, and that's really the source of their structural efficiency. Now here's the form that I used to cast this concrete model. And as you might be able to tell, I built the form by first cutting out two parabolic shapes from plywood and mounting them on a base. And then I actually created the surface that I cast the concrete on by stretching masking tape from plywood shell to plywood shell and stretching it along a diagonal path. What's so significant about this shape is that despite its complex form, the individual strips of tape that form that overall shape are in fact perfect straight lines. And you can see that very clearly when I simply take my ruler and lay it along one of those pieces of tape. And you can see that there's no gap at all between the ruler and the tape, indicating that despite this complex double curvature, the tape itself, and therefore the entire form, is actually made up entirely of straight lines. And just to prove the point, here's the Chapel Lomas de Cuernavaca under construction. And you can clearly see that all of the wooden formwork that was used to temporarily support the concrete before it cured is made entirely of straight boards that didn't need to be bent in order to create the formwork. So with this as background, let's look at some great buildings that use all three types of curved shapes as the basis for thin shell roofs. The precursor of modern thin shell structures is a building that you probably wouldn't have associated with this category. St. Paul's Cathedral in London, built between 1675 and 1710. Now, as a thin shell, the Dome of St. Paul's is certainly not on par with Chapel Lomas de Cuernavaca. It's considerably thicker. Yet it represents such a revolutionary step in that direction, and such a significant departure from previous domes, that it's worth including here. One of the main reasons that St. Paul's has such an unexpectedly modern character can be found in its extraordinary design team, Christopher Wren and Robert Hooke. Now, we typically think of Christopher Wren as one of England's finest architects, but he was also an accomplished astronomer, mathematician, and physicist, and he brought a distinctly scientific mindset to the design of St. Paul's. In 1669, Wren was installed as the King's Surveyor of Works, with the rather challenging mission of supervising the reconstruction of the entire city of London following the Great Fire of 1666. He ultimately rebuilt 51 churches in the city, but St. Paul's was by far his most spectacular achievement. This achievement was aided in no small part by Wren's chief assistant, Robert Hooke, that brilliant scientist who's taught us so much about the elastic behavior of materials. In our lecture on cables and arches, we learned about Hooke's other great contribution to engineering mechanics, his discovery that the catenary is the most structurally efficient shape for an arch. And Hooke convinced Wren to apply this discovery for the very first time in history in the dome at St. Paul's. And here we see the result of that decision, depicted in an original cross-section drawing of the dome. This is the principal element, a brick shell shaped like a rounded cone, which directly supports that immense 1,000-ton stone lantern above. And note that the cone, combined with the supporting drum and the piers down below, forms a fairly good approximation of Hooke's inverted catenary. Indeed, several of Wren's early design drawings actually show this curve sketched in, right on the page, in Wren's own hand. Of course, a conical dome wouldn't have worked architecturally for this English Baroque-style building. So Wren added two more domes, one inside and one outside, strictly for aesthetic purposes. The inner dome is a thin brick shell, which carries only its own weight, but it presents that proper hemispherical appearance from inside the cathedral. And the outside dome is actually a lead-covered timber structure that's supported directly on top of that structural brick cone and protects it from the elements. In between is the true structural element, the true load-carrying dome, the brick cone, hidden entirely from view. Now, with its 102-foot span, the Dome of St. Paul's was certainly not the world's largest, but it was one of the most ingenious and far more economical than any previous domed structure. Its thickness to span ratio is 1 to 37, compared with 1 to 21 for Brunelleschi's dome and 1 to 11 for the Pantheon, as this diagram illustrates. From this comparison, you can see that Wren and Hooke grasped the benefit of thinness in a dome structure. More importantly, they gave us a glimpse of possibilities that would only really be fully realized 2 full centuries later. The next major development in thin shell structures was the timbral vault, which originated in a traditional medieval Spanish masonry technique, but was modernized and brought to the U.S. in 1881 by a Catalan architect named Rafael Guastavino. Though they may look like heavy stone masonry, Guastavino vaults are actually composed of several layers of ceramic tile, each less than an inch thick. These layered shells were used to create long-span roofs and intricate vaults of great strength and lightness, using no temporary formwork whatsoever. They were constructed by edge gluing the lower layer of ceramic tiles together with a fast-setting gypsum cement, and then adding upper overlapping layers of tile on top of them with stronger conventional mortar. Ultimately, the thickness to span ratio of these shells was typically around 1 to 50, which is not quite eggshell thin, but quite impressive for a system that requires no temporary supports whatsoever. Examples of Guastavino thin shell vaults and domes can be found in famous buildings all over the U.S., like the Boston Public Library, designed by McKim, Mead, and White. Union Station in Pittsburgh, designed by Daniel Burnham. The incredibly beautiful Oyster Bar in New York's Grand Central Station. The neo-Gothic vaulting of the Cadet Chapel at West Point. And even the Great Hall at Ellis Island, which Guastavino's son reconstructed in 1917 after having entered the United States through that very same building 36 years earlier. Rafael Guastavino died in 1908, and he's buried in the Basilica of St. Lawrence in Asheville, North Carolina. He designed this building, and the dome of the basilica, shown here, is one of his finest works. Now, in the 1920s, the Great Revolution in thin shell structures began in Germany. The Zeiss Corporation, which made optical equipment, decided to build a state-of-the-art planetarium on the roof of one of its buildings in the city of Jena in Germany. Zeiss wanted to construct a perfectly hemispherical interior surface for the planetarium, and that surface needed to be composed of flat facets on which an array of projectors could display the stars and planets with no distortion. The completed dome structure would need to be extremely light because it was being built on top of an existing roof that hadn't been designed to support an additional structural load. Now, this project was assigned to Walter Bauersfeld, the chief design engineer at Zeiss. Bauersfeld's experience was actually in optical systems. He had no background at all in structural design. Yet this turned out to be a significant advantage because he had no preconceptions about how the dome should be built. He approached the problem from first principles rather than from established methods. Bauersfeld's first challenge was a geometry problem. He needed to identify a polyhedron that would approximate a sphere. In collaboration with a professor of botany at the University of Jena, he identified a microorganism, a type of sponge classified as a radiolarian, shown here, that's shaped like a perfect sphere, composed of hexagons and pentagons. This geometry would become the basis for Bauersfeld's dome. The hexagons and pentagons would define the flat facets, and then their boundaries, subdivided into triangles, would define a network of steel reinforcing bars. And if this combination of hexagons and pentagons seems familiar, well, it's probably because you've already seen it in the modern soccer ball, which uses exactly the same geometric configuration. I wish I had a soccer ball around to demonstrate for you. Oh, here's one. And as you can see, we have pentagons, which are the black facets of the ball, and also hexagons, which are the white facets. By the way, this ball configuration was first used in 1950. So, in answer to that famous question, which came first, the soccer ball or the Zeiss dome, the answer is most definitely the dome. Bauersfeld's final design for the dome specified a 38-foot diameter hemisphere framed by 3,480 steel rods, shown here. These elements were manufactured to an accuracy of a few thousandths of an inch, a reflection of Zeiss's standards of precision for optical equipment. Bauersfeld then collaborated with a structural engineer, Franz Dischinger, to build a concrete shell that would cover the steel framework. Dischinger devised a process that involved spraying concrete onto a wire mesh backed up by a movable form. And in fact, you can actually see that movable form mounted on the dome in this photo. And this photo shows the application of sprayed concrete, a system called gunite in modern construction. Now, in designing the concrete shell, Dischinger chose a thickness ratio of 1 to 130 because it's the same as an eggshell. And so for the second time on the same project, a natural form became the model for an engineered form. The Zeiss Planetarium was the world's first true geodesic dome. 30 years later, Buckminster Fuller would patent his own geodesic dome, but it was really fundamentally no different than the one designed by Bauersfeld in 1922, except for Fuller's use of a lightweight cladding system that wasn't available in Bauersfeld's time. The Zeiss dome was so successful that Bauersfeld, Dischinger, and another associate named Ulrich Finsterwalder refined their system and went into business building thin shell structures all over Europe. They eventually expanded their repertoire to include thin shells of every conceivable form: cylindrical, saddle-shaped, rectangular, and polygonal. They also developed sophisticated analytical methods, validated with model studies and measurements of in-service structures to ensure that the designs themselves were safe and serviceable. As the reputation of their system spread, it began influencing designers in other parts of the world. In 1932, Anton Tedesco, an associate of Dischinger and Finsterwalder, brought their technology to the United States. Now, this was the Great Depression, and there wasn't a lot of large-scale commercial construction happening, yet the prospect for significant cost savings with the thin-shell construction eventually brought the Hershey Chocolate Company to Tedesco's firm to request a design for a new sports facility. The result was the Hershey Park Arena in Pennsylvania, completed in 1936. Today, we may take this building for granted. Its simple cylindrical shape resembling a Quonset hut or an airplane hangar. But in 1936, this was truly an extraordinary structure, the world's longest spanning cylindrical shell. In 1935, in Spain, Eduardo Torroja created one of the earliest major high-par concrete shell structures, the innovative concrete canopy over the seating area at Madrid Hippodrome. These incredible cantilever shells span over 40 feet, and each is about 5 inches thick at its base, but only 2 inches thick at its outer edges. This structure suffered a severe bombardment during the Spanish Civil War in the late 1930s. Explosions punched numerous holes through the concrete shells, but the structure stood firm. And those holes were simply patched up with concrete, and that canopy remains in great condition today, a testimonial to the strength of the high-par shell. These early successes led to a profusion of important thin-shell developments in the years following World War II. In Germany, Ulrich Finsterwalder was still going strong, designing an extraordinary concrete high-par roof of the Karlsruhe Schwarzwaldhalle, a 4,500-person arena constructed in 1953, and still in use today. During this period, the Spanish architect Felix Candela created hundreds of thin-shell structures of incredible variety, mostly in Mexico. These structures ranged from the simple chapel Lomas de Cuernavaca to complex combinations of multiple high-par shapes. This building at the City of Arts and Sciences in Valencia, Spain, was built in the 1990s, but it's a near-exact copy of a revolutionary structure Candela built in Mexico in 1958. Its wonderfully distinctive form consists of 4 intersecting concrete high-pars, only about 2 inches thick. Candela also worked out an entirely different arrangement of 4 high-par shapes in a simple yet beautiful modular roof system called a high-par umbrella. And 50 years later, this same system was used for the overhanging roof of the terminal building at Newark International Airport, shown here. Some of these concrete umbrellas span 90 feet. Another important pioneer in thin-shell construction was the Italian engineer Pier Luigi Nervi. His greatest innovation was a new construction technique which used thin layers of concrete and wire mesh to create modular elements, which were then assembled together using cast-in-place concrete connections. Nervi called his new composite material ferrocemento and used it in a number of extraordinary structures, like the intricately ribbed dome of the Palazzo dello Sport in Rome, built for the 1960 Olympics. Each rib of this 330-foot diameter shell was assembled from a series of V-shaped ferrocemento modules, less than 1 inch thick. Nervi went on to demonstrate the versatility of his new technology by building sailboats and motorboats from ferrocemento. And the spirit of Nervi lives on today in the National Collegiate Concrete Canoe Competition sponsored by the American Society of Civil Engineers. In this competition, civil engineering students design, build, and race concrete boats like this one. And those who do manage to cross the finish line without sinking come away with a keen appreciation for the strength and efficiency of thin-shell structures. In the U.S., some of the finest thin shells are found in the work of Eero Saarinen during the 1950s and 60s. In 1953, Saarinen used a spherical thin-shell dome on a triangular plan in his Kresge Auditorium on the campus of MIT. And in the extraordinary Trans World Flight Center at New York's John Fitzgerald Kennedy Airport, he exploited the sculptural quality of concrete to create forms unprecedented in architecture, symbolizing the excitement of flight. Nervi also did some fine work in the U.S. including San Francisco's Cathedral of St. Mary the Assumption, completed in 1971. The roof of this structure is composed of 4 vertically oriented high-par segments. Unfortunately, some observers have noticed a resemblance between this uniquely shaped roof and the agitator of a washing machine. And so this great building is sometimes called Our Lady of Maytag. No discussion of concrete shells would be complete without the Sydney Opera House. This great building was the product of a design competition conducted in 1955 and judged by Eero Saarinen, whose contributions to the world of thin shell structures we've already seen. And the winner was a Danish architect named Jorn Utzon, whose creative vision took nearly 20 years to realize after that competition. Construction began in 1959 and wasn't complete until 1973. But it was certainly worth the wait, as the completed Sydney Opera House is widely regarded as one of the 20th century's most iconic structures. Its most recognizable feature is a series of curved shells that form its roof. A fascinating aspect of these shells is that despite their varying sizes and orientations, they're all spherical segments of exactly the same radius. In developing the design, Utzon worked closely with the construction contractor, Ove Arup, to devise a geometric configuration that would achieve the desired aesthetic effect at an affordable cost. They considered various parabolic and ellipsoidal schemes before finally settling on the single radius spherical geometry of the final building. This configuration proved to be the only economically feasible alternative because it allowed for the standardization of structural components in all of the shells. But perhaps the most important aspect of these iconic shells is that they really aren't shells at all. At least not in the same sense that Guastavino's tile vaults and Candela's concrete roofs are shells. Yes, they are invariably called shells because, well, they look like shells. But from an engineering perspective, a true thin shell is a continuum, a single structural component that's been formed into a complex curved shape, typically from monolithic concrete. Utzon, the designer, originally intended to use true thin shells for the roof of the Opera House. But this concept ultimately proved to be structurally infeasible. The planned shells were so tall that wind load rather than self-weight dominated their design. And a thin shell couldn't be made strong enough or stiff enough to resist these kinds of loads. This is true in the Sydney Opera House for the same reason that I was able to apply a tremendous amount of compressive load to the surface of my egg as long as I applied it over the entire surface. But if I use the same egg and now simulate the application of wind loading, which is now being applied from only one side, the strength of the egg is significantly reduced. It's, indeed it is. And so, the roof of the Sydney Opera House is actually composed of 2,400 discrete precast concrete ribs, which are thick enough to resist that sort of bending caused by lateral wind load on the roof. You can see the ribs here, inside the roof. And these ribs support 4,000 individual concrete panels, which were precast on the ground and then attached to those ribs during construction. This system of interconnected elements would actually better be regarded as a frame than a shell. Whether frame or shell, the Sydney Opera House is yet another dramatic example of the versatility of concrete, and in a broader sense, of a great structure's power to inspire. It's hard not to see a hint of the Sydney Opera House in one of the 21st century's most dramatic buildings. Auditorio de Tenerife in the Canary Islands, designed by Santiago Calatrava. The auditorio's unique cantilever high-par shell dramatically evokes a wave breaking over a reef, beautifully illustrating the thin shell's extraordinary potential for architectural expression. This cantilever high-par is among the most distinctive structural elements we've encountered anywhere in this course, and yet I think you can see that it actually carries load in essentially the same way as that curved piece of paper I demonstrated at the very start of today's lecture. Just like that. And like the piece of paper, Calatrava's auditorio roof gains its strength and its stiffness from its curvature. So, in all such structures, aesthetic beauty and structural strength derive from exactly the same source, the curved shape of the shell. It's this perfect marriage of form and structure that makes seeing and understanding thin shell structures so uniquely satisfying. Thank you.